Hey there, Math 20-1. Today I'm going to be taking you through lesson 1.3 on radical equations. So this is the second part of our unit. We've worked with radical operations, learning how to, or reviewing how to break down a radical, and then how to do operations like adding, subtracting, multiplying, and dividing, how to rationalize. Now we're going to look at how to actually solve. And so I want to be clear, when we are solving an equation, that means we have an equal sign. We're actually trying to determine the value of a variable. When we're working with rational operations, we are simplifying. We don't actually have an x equals. We're just taking an expression, because there's no equal sign, and breaking it down into its simplest form. So today with equations, there's two parts. We're going to start by looking at restrictions, and then we're going to move on to the actual solving of the equation. For a lot of students, sometimes the restrictions is the more challenging part of the lesson. So what you might want to do is actually jump ahead to example 2 and follow along the algebra piece, get really good with that, and then come back and look at the restrictions piece, and it might seem a little less confusing as you're working through it. So let's first get started by talking about what makes a radical equation. First of all, we've talked about an equation having to have an equal sign. A radical equation is an equation that has at least one radicand containing a variable. So the radicand is the piece that's underneath the root sign. And so we can be working with square roots and cube roots and so on. In this lesson, we are only looking at square roots. The radical equations lesson that we're doing today is only half of the lesson. In Unit 1, Radical Expressions and Equations, we are just going to look at radical equations that do not require factoring. When we get further into the course and we finish or get near the end of the quadratics unit, Unit 5, then we're going to look at radical equations again. We're going to revisit this concept, but in that case, some of our examples will also require factoring. So let's talk first about restrictions. When we are working with math, depending on the expression that we're working with, we may have restrictions, values that x cannot be. When we're dealing with radicals, if you remember, we can't ever square root a negative. So we have to figure out what values would make the radicand or the expression underneath the radical sign negative. And whatever those values are what we call restricted values. We can't have them. And so this ties into domain when we're talking about domain and range. Right now, we're just going to talk about the restriction. We're not going to write it as a domain. Later on again in the course, when we get to Unit 6 and we're looking at rational expressions and equations, we're also going to be dealing with restrictions there. But these restrictions that we're talking about here are specific to radicals. So again, as was just mentioned earlier, we cannot square root a negative. So that means the radicand, and the radicand is the part that's underneath the root sign. We cannot have a negative radicand. That means that the radicand has to be positive. So we take our radicand right here. That's our negative 3x. We say that it has to be greater than or equal to 0. So that's the way that we say that it needs to be positive. And then we're going to just solve for x. Just like we would if that was an equation, now we have an inequality statement. So I have negative 3x has to be greater than or equal to 0. Well, to get x by itself, we need to divide by negative 3. Now there is this special rule. When I'm dividing or multiplying by a negative and I'm working with inequalities, my sign has to flip. And so that just has a lot to do with the properties of negatives and positives. I won't get into that right now, but just be aware that anytime you have to multiply or divide by a negative when we're working with inequalities, your sign is going to flip. So here I've divided negative 3x by 3. Those are going to cancel out. 0 divided by negative 3 is 0. And so because I divided by a negative, my sign flipped from greater than or equal to less than or equal to. So my restriction just says that in order for this expression to work, x has to be less than or equal to 0. All right, so let's take a look at some examples here. For example 1, we're not actually going to solve these equations. We are just going to look at what our restrictions are. So again, when we're looking at restrictions, we're just looking at the radicand. So here my radicand is 4x plus 2. So we say 4x plus 2 must be greater than or equal to 0. To get x by itself, we're going to subtract 2. So 4x is greater than or equal to negative 2. And then we need to get x by itself. We're going to divide by 4. And when we do that, I'm going to have x is greater than or equal to negative 1/2. Now, in this case, we were not dividing by a negative, so our sign stays exactly the same. So when we get into solving the equations, if I get a value that is not greater than or equal to negative 1/2, I can eliminate it and say that answer is not possible. Okay, for our next example, our radicand is 2 minus 5x. So 2 minus 5x has to be greater than or equal to 0. Now we can move the 2 or we can move the 5x. You saw in our earlier example, when I have to multiply or divide by a negative, I got to flip that sign. I don't like having to always remember those rules, so I'm actually going to move the 5x. So I'm going to keep the 2. When that 5x comes across, it's going to become positive. So we now have 5x. And in order to get x by itself, I'm going to divide by 5. Now, because I was not dividing by a negative, I don't have to flip my sign. So I have 2 over 5 is greater than or equal to x. Generally, we write our final answer with the variable on the left. So I'm going to write my x, I'm going to write my 2 over 5, and if you notice, the alligator is eating the 2 over 5, so that means I want that to still be the same when I write my final expression. So here I have x is less than or equal to 2/5. Now moving on to our third example, what you'll notice is that I have two radicands. That means I need to check both expressions. So for the first one, I have x plus 2. So x plus 2 is greater than or equal to 0. To get x by itself, I'm going to subtract 2 from both sides. So I have x is greater than or equal to negative 2. And for my other expression, I have 3 minus x. 3 minus x is greater than or equal to 0. Again, I'm going to move that x. I just don't like working with negatives. So I'm going to have 3 is greater than or equal to x, which means x is less than or equal to 3. Okay, so now that I have my two expressions, I need to see how they relate to each other. And the best strategy is to sketch a number line. So I'm going to draw a number line. I'm going to mark negative 2 and positive 3. And then I'm going to highlight the sections of the number line that represent my expressions. So for the first expression here, I have x is greater than or equal to negative 2. So that means the negative 2 is included and all of my numbers are getting bigger. And then for the second expression, I have x is less than or equal to 3, which means the 3 is included and all of my numbers are getting smaller. If you notice now, there's a section of the number line that is overlapping colors, and that's where my solution is going to be. So I have x is greater than or equal to negative 2, x is less than or equal to 3, but that's not my final answer. So on the number line I had x is greater than or equal to negative 2 and x is less than or equal to 3, but my final expression needs to incorporate both of them. So it's saying that all of my possible solutions fall between those two numbers. And so we would say my x values go from negative 2 to positive 3. All of my x values are in between. And as I move from negative 2 to positive 3, my numbers are getting bigger. So I'm going to show you that one more time using a strategy that I use. I typically will write my lowest number, my highest number. I'll put my variable in between because it's saying that all of my x values are between negative 2 and positive 3. And then I just make the alligator eat the bigger number. So as I'm moving from lowest to highest, the numbers are getting bigger. And there would be my final restriction. What that means is that when I solve the equation and I get my answers, if my answers do not fall between negative 2 and 3, I can eliminate that as a possibility and say, sorry, that answer doesn't work. All right, so we're going to move into the second part of this lesson, and this is where we're going to look at actually solving the equations. And if you remember when we're doing algebra, we're basically looking at order of operations and working in reverse. So it's bed mass backwards. So our ultimate goal is to start off first by isolating our radical. We want to get it by itself. If I have two radicals, ideally I want them on opposite sides of the equation. Then I want to eliminate that radical, and I might have to repeat that process a couple times. Now, as part of solving an equation, you always need to list your restrictions. And then as a final step, you also have to check for extraneous roots. So when we're solving radical equations, there's always going to come a point where we have to square both sides. And sometimes we actually have to do that more than once. And as part of that process, we're essentially deriving an equation, and that's going to lead to what's called an extraneous root. An extraneous root is an answer that we got. We did all the math correctly, but when we sub it back into the equation, it actually doesn't make it true. Okay, so I'm just going to take a brief aside here for a minute, and I want to remind you that if I'm talking about root x, that just means I'm talking about the positive root. And so what I mean by that, if I have an equation that says x squared equals 16, my first step is going to be to square root both sides. Now, if you remember, whenever you square root a number, you need to remember that there are two possible answers, both the positive and the negative. So the square root of x squared is just x, but the square root of 16 is plus or minus 4 because 4 squared is 16, but so is negative 4 squared. And so when I'm square rooting a number as part of an algebraic process, I have to consider both the positive and negative. All right, so let's take a look at our first example here. We have the square root of x plus 1 equals 4. Before I get into the solving, I always want to remember to check for my restrictions. So here I'm going to have x plus 1 is greater than or equal to 0. Remember, it's always the radicand is greater than or equal to 0. Then we have x is greater than or equal to negative 1. I don't need to do anything else with that right now. I'm just going to leave it there. Then I want to actually solve the equation. Now, step one, whenever we're solving these equations, is to isolate your radical, meaning get the radical by itself. And so here what we're going to do is square both sides, because that's the opposite operation of square rooting. So if I have something that's being rooted and I square it, I've canceled out those two operations. So here now I'm going to have x plus 1 equals 16. And again, make sure that you're doing the same operation on both sides. Often what will happen is someone will write x plus 1 equals 4, and then now they've made a silly mistake. So to get x by itself, we're going to subtract 1 from both sides. So you got 16 minus 1 is 15. Now, if only we could be done. Like I said before, when we square both sides, we're actually creating a derived equation, and so we always, always, always have to check for extraneous roots. And the way that we're going to do that is with a left side, right side chart. We can't establish equality until we've actually subbed in. So a left side, right side chart means we take the left-hand side of the equation. In this case, that's the square root of x plus 1. And the right-hand side of the equation, which is 4, and then we're going to sub in the value that we just got. So in this case, that's 15. So I'm going to have 15 plus 1, all square rooted. Well, 15 plus 1 is 16, so we've got root 16. Square root of 16 is 4. They both balance. I can give it a check mark, and now I can actually box my answer as a solution. All right, moving on to part B. Here we have root x minus 1 minus root 2x plus 3 equals 0. So step one, always look for those restrictions. So we have x minus 1 is greater than or equal to 0, x is greater than or equal to 1, and then we have 2x plus 3 is greater than or equal to 0. Well, to get x by itself, we're going to subtract 3 and then divide by 2. So x is greater than or equal to negative 3 over 2. Now, once again, we're dealing with two expressions, so I need to draw a number line. So drawing our number line here, we're going to put negative 3 over 2, and then we're going to put 1. Sketching that out, x is greater than or equal to 1, so that's going in this direction. And then x is greater than or equal to negative 3 over 2. Now, if you notice in this case, both lines are going in the same direction. Our overlap actually happens after we pass the 1. So that means it doesn't matter if it's bigger than negative 3 over 2 because it has to be bigger than 1. So we eliminate this as a restriction, and our final restriction is just x is greater than or equal to 1. All right, so let's move on to solving the equation. We have two radicals here, so ultimately we want them on opposite sides of the equation. So I'm just going to move this over, and that's going to give me root x minus 1 equals root 2x plus 3. Now I can square both sides, and that gives me x minus 1 equals 2x plus 3. Now, continuing on with the algebra, I want to get all of my variables on one side of the equation and my numbers on the other. I personally do not like working with negatives. That's usually where I make my mistakes. So I'm going to subtract x from both sides and then subtract 3 from both sides. That's going to allow my variable to stay positive. Negative 1 minus 3 is negative 4, and 2x minus x is just x. So my final answer here is that x equals negative 4. So now we've got x equals negative 4, but we can't say for sure whether that works or not until we sub it back into our original equation. So this is the part where we're checking for extraneous roots. So we're going to draw our left side, right side chart. Now, technically, we can actually do our left side, right side chart using our second step, as long as whatever step you're using happens before you had squared both sides, then you're good. So I'm going to start with step 2, where I've got root x minus 1 and then root 2x plus 3. And that's more just for simplicity for myself. I generally say to always start with your original equation, but I'm going to just take that second step where I've already isolated my radicals, but it's before I've squared both sides. So I'm going to sub in that negative 4. So that's going to be negative 4 minus 1, all square rooted. And on the other side, I'm going to have 2 times negative 4 plus 3, all square rooted. So on the left-hand side, that's going to give me the square root of -5. And on the other side, I'm going to have 2 times -4 is -8 plus 3 is the square root of -5. Now you might be looking at that and going, hey, great, we got the same answer on both sides. We're all good. It all matches. But we also know that we cannot square root a -5. So this is not a possible answer. We also could have already said this doesn't work because if you notice, our restriction says that x has to be greater than or equal to 1. This is not greater than or equal to 1. So we could have actually eliminated it and said that it was extraneous before we even got to the LSRS side. So when we know an answer doesn't work, we're going to cross it out and either write EXT or write the full word extraneous. But it's always important that you make it clear whether something is an answer or not an answer. All right, moving on to our last example here, we have root x plus root x minus 4 equals 4. Again, we have to check for our restrictions. So x is greater than or equal to 0, and x minus 4 is greater than or equal to 0. That means x is greater than or equal to 4. Now, at some point, you're going to have enough experience with this. You may not have to draw that number line, but in the beginning, I would strongly encourage you to do so. So here we're going to have 0 and 4. I know that as I'm getting greater than 0, I'm moving to the right. Greater than or equal to 4, I'm moving to the right. That means in both cases, I have to be bigger than 4. So we ignore the 0, cross it out, and our restriction is x is greater than or equal to 4. Now moving on to the solving portion. This is one that's a little bit trickier because we're going to have to repeat some processes. So I have root x plus root x minus 4 equals 4. Step number 1, isolate your radical. I usually say isolate the more complex radical. So root x is a little easier to work with than root x minus 4. So I'm going to subtract root x from both sides. So that's going to give me root x minus 4 equals 4 minus root x. Now step 2 is to square both sides. Now remember common mistakes. If I have 4 minus root x all squared, that does not mean just bring in the 2. It means 4 minus root x times 4 minus root x, and then we're going to use the distributive property. On the other side, the square roots canceled out, so we're just left with x minus 4. So we're going to multiply this out. X minus 4 equals 4 times 4 is 16, minus 4 root x, minus 4 root x, plus root x squared. Well, if I'm multiplying a root x times a root x, I'm just going to be left with x. Now, if you needed to write that out, we've got root x times root x gives me root x squared. And we can notice that the squared and the square root cancel each other out to give me the x. So continuing on with the algebra, I'm going to start by simplifying that right-hand side. So the left stays the same for now. I've got x minus 4 equals 16 minus 8 root x plus x. So I still have a radical in the equation, and so now we go right back to step number 1, isolate the radical, and then continue it from there. So I'm going to subtract x from both sides, and at the same time, if you wanted to, you could subtract your 16, because what we want to do is get that negative 8 root x by itself. So x minus x is gone, negative 4 minus 16 is negative 20, and then on the other side, I've got negative 8 root x. So now at this point, you actually have two options. If I were to divide negative 20 by negative 8 and get a nice number, like no fractions, no decimals, then I would absolutely go for it. In this case, though, negative 20 over negative 8 is not a nice number. It's going to be a fraction. So you do have the option of just squaring both sides at this point. And so if you do that, you need to remember that you're not just squaring the root x, you're also squaring the negative 8. This is not like what we had above here. There's no plus or minus in between. It's not a binomial, so we can just have negative 8 squared and root x squared. So negative 20 all squared, be very careful on your calculator. If you put negative 20 squared in your calculator without brackets, you're going to get the wrong answer because your calculator is only going to apply the 2 to the 20 and not to the negative. So if you want the negative included, you need to have brackets. So negative 20 squared is going to give us 400. Negative 8 squared is 64. Root x squared is just x. So now I've got 400 over 64. If I put that into my calculator, 400 divided by 64, and then I math frac that because we want to keep our answer exact, not write it as a decimal, that gives me 25 over 4. So I'm going to have 25 over 4. Now, certainly in your calculator, if you want to use 6.25, that's fine. But as your answer, it needs to be 25 over 4. Now, I got a little ahead of myself boxing that question because we need to check, is it extraneous or not? So this is again where we're going to set up our left side, right side chart. So as we create this chart, we've got the left-hand side, the right-hand side. Remember, the left-hand side was on the left side of the equation. So that's root x plus root x minus 4, and the other side is 4. So I've got root 25 over 4 plus the square root of 25 over 4 minus 4. So for now, I'm just going to leave this as root 25 over 4. In the next expression here, my radicand is 25 over 4 minus 4. Well, when I calculate that out, that's going to give me root 9 over 4. These are nice numbers I can actually do in my head. Root 25 over 4 is the same as root 25 over root 4, so that's going to be 5 over 2. And root 9 over root 4 is 3 over 2. And so if I add 5 over 2 plus 3 over 2, that's giving me 8 over 2, which happens to be 4. And that tells me that my left-hand side and my right-hand side are equal. So this answer is, in fact, correct. All right, so we're moving on to the Let's Practice section of the lesson. What I want you to do is I want you to pause the video, try solving any two of the radical equations or challenge yourself in trial, and then you're going to come back and check your answers. Remember that for every single equation, you need to identify your restrictions, solve for your x value or solve for your variable, and then check for extraneous roots with your left side, right side chart. All right, go for it. And welcome back. Let's take a look at your answers. Now there's a lot going on the screen here, but let's take a look at each of the pieces. First of all, we start off with looking for our restrictions. So 3x plus 1 is greater than or equal to 0, and x minus 1 is greater than or equal to 0. They're both going in the same direction. They're both saying x is greater than or equal to. So we're going to take the higher number. X is greater than or equal to 1. The other one gets eliminated. Looking at the algebra, first thing we wanted to do was isolate the radicals to move them to both sides of the equation. And then I wanted to get the coefficients simplified. I chose to divide by 2. That avoids some fractions. So we divided by 2 on both sides, and that left me with root 3x plus 1 and 2 root x minus 1. Now I'm going to square both sides. So I have 3x plus 1, and remember when I'm squaring both sides here, the 2 also needs to be squared, so I have 4 times x minus 1. Don't forget those brackets, or you'll miss bringing that 4 through. So we have 3x plus 1 equals 4x minus 4. A very common mistake is for students to write 3x plus 1 equals 4x minus 1, either because they missed the brackets or because they missed bringing it through the brackets, bringing that coefficient through the brackets. So just be very, very careful about silly mistakes. All right, so as we continue on with the algebra, I subtracted 3x from both sides and added 4 to both sides. So we have x equals 5. Then we plugged everything into our left side, right side chart, and we see that 8 equals 8. So x equals 5 is a solution. Moving on to question number 2, again, we start with our restrictions. 2x minus 1 is greater than or equal to 0, so x is greater than or equal to 1/2. Then for the algebra, we want to isolate that radical as much as possible. So I've added 7 to both sides, and then we divided by -4. Be very careful not to miss that negative. Gives me -6. And then when I square both sides, I'm going to have 2x minus 1 equals 36. And again, be careful about that calculator issue. Make sure your negative is in brackets if you're putting it in your calculator. Now I have 2x equals 37. We're going to have 37 divided by 2. I know it's not a nice fraction, but we still need to check our answers. When we sub in, we notice that we get -31 on one side and 17 on the other. So this is not a solution, and we can say that it's extraneous. Now, if you remember earlier when I was talking about some ways you might recognize an extraneous root coming, you could have done that at this step here. Notice that they've got a positive root equaling a negative value. So I know already by step 2 that I'm going to have an extraneous root. And moving on to our third example. Again, I've done my restrictions off to the side. So x is greater than or equal to -45 or greater than or equal to 0. Well, 0 is bigger than -45, and the signs are going in the same direction, so I have x is greater than or equal to 0. Now moving on to the algebra piece, notice that radicals are both on opposite sides of the equation already, so I just need to square both sides. Remember that we're squaring a binomial, so it's important to remember that we need to multiply it out using the distributive property. So that's going to give us x plus 5 root x plus 5 root x, which is 10 root x, plus 5 times 5, which is 25. And on the right-hand side, we have x plus 45. Again, when we subtract x from both sides, we notice our x's cancel. This won't happen with all of our equations. We just lucked out again. And now I've got 10 root x plus 25 equals 45. When I take 45 and subtract 25, that gives me 20. So I've got 10 root x equals 20. Dividing by 10 on both sides, I'm going to have root x equals 2. Now again, I've got the radical isolated. I can square both sides, and that gives me x equals 4. When I sub everything in to check for extraneous roots, I see that both sides equal, so x equals 4 is a solution. So moving on to our final 3 examples, we're going to look at some applications that involve solving radical equations. So we have v equals root PR. We're told to find p or calculate p, and we're given v, and we're given r. So we're going to start by writing our formula. V equals the square root of p times r. And then we sub in the values that we know. So we have v equals 120. And then the square root of p times 30. So I can even write that as 30p. My radical is already isolated, so I'm going to square both sides. 120 squared is 14,400 equals the square root of 30p. So we've got 30p now. And then my next step is to divide by 30 on both sides. That's going to give me p equals 480. Now we weren't given any units, so at this point we're just going to leave it as p equals 480. Now for these 3 application questions, we're not asked to do restrictions, so I have not done that. However, it's still always a good idea to take your final answer, plug it back in, and make sure that it works. So I'm going to just do this on the calculator. I've got 480, so I'm going to take the square root of 480 times 30, and it should give me 120, and it does. All right, moving on to example 4, we're asked to determine the radius of a sphere, we're given the surface area, and we're given a formula. So here we have SA equals 4 pi r squared, and we're told that the surface area is 200 centimeters squared. We're also asked to round our answer to the nearest tenth. So we're going to take the 200 and sub that in. 200 equals 4 pi r squared. Now what you've probably already noticed is this is not a radical equation, and it's not, but we are going to end up working with radicals, and it'll give us an opportunity to get some practice with breaking down radicals. So now that we have our equation written, we need to get r squared by itself. We can do that by dividing by 4 and then dividing by pi, or we can divide by them both at the same time. What you need to be very careful of is when you're doing this on your calculator, you can't just go 200 divided by 4 pi. You need to go 200 divided by 4 pi in brackets. What that looks like is 200 divided by, in brackets, 4 second function pi. If you don't use those brackets, what's going to happen is you are actually going to go 200 divided by 4 and then multiply by pi. So if you notice here, I go 200 divided by 4 pi. My calculator is scientific, so that means it's going to follow order of operations. It's going to go 200 divided by 4, which is 50, and then it's going to multiply by pi. Notice 50 pi is the same thing. So again, just be very careful with your calculator. Now this particular question is asking us to round to the nearest tenth, so you can start turning it into decimals at this point, but I'm going to keep it exact because I want to show you the difference between an exact answer and a rounded answer. So here we have 200 divided by 4, which is 50, so that's 50 over pi equals r squared. To get r by itself, we're going to have to square root both sides, and that's going to give us the square root of 50 over pi equals r. Now, if I was asked for an exact root, I need to break that down. So remember, if I have root 50, that's the same as root 25 times root 2, which breaks down to 5 root 2. So that would give us 5 root 2 all over root pi equals r, which is the same as saying 5 times root 2 over pi. So these would be considered exact values. In 20-1, expect that you're going to be asked to keep most of your answers exact. You're not necessarily going to be rounding as much as you did in 10C. Now for this particular example, we are actually asked for a rounded value. So what we do is we can go to our calculator and we can have second square root 50 divided by pi. You could have also used that earlier step where you had the 200 divided by 4 pi in brackets. It's going to give us 3.989. Remember, rounding to the nearest tenth means that we want the 1 decimal place. So we look at the 9 and then look at the number directly to the right. That's an 8. Tells us we need to round up. There's a chain reaction and we end up with 4.0. So that gives us the 4.0 centimeters. Make sure that you have the centimeters for both your rounded and your exact values. So again, the 5 root 2 over pi would be exact. The 4.0 would be our rounded value. And in this case, that's the one the question is asking for. So taking a look at our fifth and final example, we're given the formula for the volume of a sphere. We're given what the volume of the sphere is, and we're asked to determine the radius. Again, in this question, we're asked to round to the nearest tenth, so that's all you need to do, but I'm going to go through the exact version as well. So we have our formula, 4/3 pi r cubed. We're going to sub in the 400, so 400 equals 4/3 pi r cubed. Now you have a couple options here in where you go. You can divide by the 4/3 and the pi at the same time. You can actually multiply by 3 and then divide by 4 pi. There's a few different directions that you can go. Ultimately, though, you want to get r cubed by itself. So if I were to look at this equation written just slightly different, I would have 400 equals 4 pi r cubed divided by 3. There it's a little more obvious to see that you can just multiply by 3 on both sides. That's going to give me 1200 equals 4 pi r cubed. Divide by 4 pi on both sides. Gives me 1200 divided by 4 is going to be 300. And then we still have a pi on the denominator. And then we have r cubed here. Now in order to get rid of that r cubed, we need to cube root on both sides. So that leaves us with the cube root of 300 over pi equals r. Now when we're cube rooting, we don't have to worry about plus minus. You'll notice if you go back to the previous example, I didn't even consider the plus minus. And part of that was because I was working with measurement and I knew that the negative answer would not be a valid answer, but it's still important to always consider plus minus. So this would be my exact value. I could go further and check to see if I can break down that cube root of 300. However, again, I know I'm being asked for nearest tenth, so let's take a look at that part. When I want to put this into my calculator, I'm going to have math 4, that's the cube root, of 300 divided by pi. Rounded to the nearest tenth, we've got 4.57. So we round to the nearest tenth, that's going to give me 4.6. So there we have again our exact and our rounded values. So exact is the cube root of 300 over pi, and then our rounded is 4.6 centimeters. Again, remember to always include your units if this is a measurement question. Since it's the rounded value that I'm being asked for, this is the one that I'm going to box. All right, guys, so that gives you lots of examples. I hope that helps. I hope you're able to use these as you work through those questions this week. If you have any questions, always reach out. Have a great day, and I will see you soon.